Welcome to our lesson on Riemann sums, a foundational concept in calculus for approximating areas and integrals. Riemann sums help us calculate the area under a curve by dividing it into multiple rectangles and summing their areas. Let me explain what a Riemann sum is. First, we partition the x-axis into subintervals. Next, we construct rectangles over each subinterval, where the height of each rectangle equals the function value at a specific point within that subinterval. Finally, we calculate the sum of the areas of all rectangles. This sum gives us an approximation of the area under the curve. There are three common types of Riemann sums. Left Riemann sum, where we use the function value at the left endpoint of each subinterval. Right Riemann sum, where we use the function value at the right endpoint. And midpoint Riemann sum, where we use the function value at the midpoint of each subinterval. Now, let's look at the formal definition of a Riemann sum. Given a function f defined on a closed interval, ab, we divide the interval into n subintervals, each with width delta x. The Riemann sum is defined as the sum of the function values at specific points in each subinterval, multiplied by the width of the subinterval. Let's work through a concrete example to understand how to calculate a Riemann sum. Consider the function f(x) equals x squared on the interval 0, 2. Let's divide this interval into 4 equal subintervals, each with width delta x equals 0.5. For a right Riemann sum, we'll use the values of f at the right endpoints x equals 0.5, 1, 1.5, and 2. The Riemann sum equals f 0.5 times delta x plus f, 1, times delta x plus f, 1.5, times delta x plus f2, times delta x. Substituting the values, we get 0.5 times 0.25 plus 0.5 times 1 plus 0.5 times 2.25 plus 0.5 times 4, which equals 3.75. As we increase the number of rectangles, our Riemann sum approximation becomes more accurate. In fact, as the number of subintervals approaches infinity, the Riemann sum approaches the definite integral of the function. This is why we define the definite integral as the limit of Riemann sums. The integral from a to b of f, x, dx equals the limit as n approaches infinity of the sum from I equals 1 to n of fc underscore a times delta x. This relationship is the foundation of the fundamental theorem of calculus, which connects differentiation and integration. To summarize, Riemann sums are a powerful tool for approximating the area under a curve. We learned about left, right, and midpoint Riemann sums, how to calculate them, and their relationship to definite integrals. As you practice more with Riemann sums, you'll develop a deeper understanding of the fundamental concepts of calculus. Thank you for watching.